Okay, this is section 7.1, accumulation and net change. This is all review, so we're just going to do a couple quick examples. The first is going back to our linear motion. So we've got a problem where we're given velocity in meters per second of a particle moving along the x-axis from 0 to 9 seconds. So we're going to do four things. First, determine when the particle is moving to the right, to the left, and stopped. So think for just a moment, what are we going to do to find when velocity is right, left, or stopped? We'll come back then and do displacement, position, and distance. Remember, these three things are very different. So moving to the right and to the left, well, the answer is down here. When the velocity is greater than 0, the particle is moving right, and this happens from 0 to 5. So what we do to solve this, and I'm sorry they didn't give me much room here, but for part A, when 10 minus 2t equals 0, we have t is equal to 5. So therefore, using a number line from 0 to 10, because that's, or 0 to 9, that's what we're looking at. At 5, we are 0. From 0 to 5, any number from 0 to 5, I get a positive. Any number from 5 to 9, I get a negative. So v of t is greater than 0 between 0 and 5. V of t equals 0 at 5. And v of t is less than 0 from 5 to 9. Okay, displacement now, that has to do with position or distance. Displacement is the integral from 0 to 9. And displacement is the net gain of a particle. So displacement is the integral from 0 to 9. Using our antiderivative and solving, we get 9 units. So during the first 9 seconds of motion, the particle moves 9 meters to the right. C asked about position. So let's go back and look at our problem. It says find the position at the end of 9 seconds if the starting position is 3. So displacement was 9. Position, we have to add 3 to that. Oftentimes they'll ask you to do this in one step. So we would be writing that the position after 9 seconds is the integral from 0 to 9, 10 minus 2t dt, plus my initial position. The last question was total distance. Now, distance is the absolute value of the integral. So now we have to take into account when it's positive and when it's negative. So the total distance is the integral using absolute value. In order to calculate that, we have to break it into our two parts, 0 to 5 and 5 to 9. Now, keep in mind that from 0 to 5, we were moving forward. Is that right? 0 to 5 was positive. 5 to 9 was negative. So I'm not sure why they didn't do that. Oh, they did do the opposite down here. So I would have written it as the absolute value of this to get our total distance. I have to look at this a little more closely. I think that this is a mistaken slide. Let's take a look. 0 to 5, 10t minus t squared. So from 5 would be 50 minus 25, and then minus 0. So that's our first part, and that is 25 units. That's our positive motion. Here we have t squared, which is 81, minus plugging in 9 here, minus 90. So that's the first piece, minus our 25, putting in our 5, minus 50. So they changed the sign there. All of this, 81 minus 90, minus 25 plus 50, it does give us a positive value. And I'm not sure why, but we do end up with 41. I'm going to need to look at that a little more closely, and let's talk about this in class. The last little example we're going to look at is consumption. An integral is a natural tool to calculate net change and total accumulation. You know, often for our integral, we're taking accumulation using something like Riemann or trapezoids by accumulating all our areas. So we can do this with more than just distance and velocity. They can be used to calculate growth, decay, and consumption. Whenever you want to find the cumulative effect of a varying rate of change, we are going to integrate. So from 1970 to 1980, the rate of potato consumption was consumption equals 2.2 plus 1.1 to the t bushels per year. This is a rate of change. So it's like a velocity, with t being years. So how many bushels were consumed? We're going to integrate. You can use a Riemann sum as well. We're not going to do that. So we are going to use the definite integral from 2 to 6, go to 0. So this is our integral from 2 to 6, and then calculating it with your calculator, we get 14.62 bushels. So the idea of using our integration for a cumulative, whether it be a distance or a consumption of potatoes or population or anything else. And that's all we're doing for this particular section.